Hello, everybody. Today we're talking about the piezoelectric energy and what it can do for the body. Um, I'll be reading an article today from the Royal Society of Chemistry. It is actually to back up what I had said in one of my lives. It's designed so that you can look at this part right here and understand and go over what I was talking about with piezoelectricity. So, piezoelectricity, a linear electromechanical coupling, is of great interest due to its extensive applications, including energy harvesters, biomedical, sensors, and automobiles. A growing amount of research has been done to investigate the energy harvesting potential of this phenomenon. Traditional piezoelectric or inorganics show high piezoelectric outputs, but are often brittle, inflexible, and may contain toxic compounds such as lead. On the other hand, biological piezoelectric materials are biodegradable, biocompatible, abundant, low in toxicity, and are easy to fabricate. Thus, they are useful for many applications such as tissue engineering, biomedical, and energy harvesting. This paper attempts to explain the basis of piezoelectricity in biological and non biological materials and research involved in these materials, as well as applications and limitations of each of the piezoelectric materials. Okay, so in addition to the rapid technological and social development of our societies, we intensely strive for a healthier life. Both areas are inherently linked. Clean and renewable energy sources that are needed to keep up with worldwide demand substantially and in the same time reduce the negative impact of global warming and environmental pollution. Alternative renewable energy sources such as biomass, solar, wind, and tidal energy are helping in the decarbonization of the power sector. Mechanical energy harvesting is one of the front runners to sustainability power micro devices. These devices play a key role in our daily lives, not only for leisure, but also for an interesting degree for monitoring and adjusting biological systems, including in vivo processes. This monitoring will be beneficial for diagnostics, for example, real time heartbeat observation, on time medical interventions, and ultimately leading to longer and healthier lives. Mechanical energy harvesting research is gaining momentum even after the nanoscale range. There is plenty of wasted mechanical energy available in the environment, waiting to be converted into useful electrical outputs. Daily human activities show possible energy harvesting examples, such as walking, talking, running, heart pumping, knee bending, driving vehicles, and etc. A promising way to harvest this wasted ambient mechanical energy is by using piezoelectricity. Piezoelectricity can provide a possible sustainable contribution as part of a bigger solution scheme to the sustainability issues. It can help to minimize the reliance on non renewable energy sources and ensure a more efficient use of natural resources. Piezoelectric research starts off by focusing on inorganic materials such as zinc oxide, barium titanate, and lead zincarnate titanate. But it later branched out to organic polymer materials such as PVDF. In 2006, Wang reduced the size of ZNO, zinc oxide, piezoelectric device to create a nano generator. In this work, nanowires were deformed by small forces, which induced electrical charge generation at the lower and upper parts of the nanowires, confirming the possibility of using piezoelectricity for energy harvesting. Piezoelectricity is not only present in inorganic compounds, but it also plays a crucial role in biological organisms. It has been reported that the piezoelectricity exists in various biological structures ranging from amino acids to tissues, and some of them has comparable piezoelectric strength to that of conventional piezoelectric material. Furthermore, organic piezoelectric materials such as collagen hold several advantages over conventional piezoelectric ceramics, including biocompatibility, biodegradability, high flexibility, low toxicity, and the ease of fabrication. Piezoelectricity in biological structures is already been explored to fabricate energy harvesting nanogenerators. However, its biggest potential lies within biomedical applications due to relatively low energy demands and a need for biocompatible materials. Currently, batteries power various implantable devices that need to be replaced at the end of their lifespan. This requires surgery, which can impose risk or complication to the patient. To overcome these limitations, it would be ideal to take advantage of energy that is wasted during the natural processes of the body. The origin of the piezoelectricity and its role in the biological structures are currently not fully understood. This impedes the development of biopiezoelectric applications. Large heterogeneity within piezoelectrical structures also limits precise control of the polarization, strength, and direction. Therefore, understanding the mechanics behind piezoelectricity in biological structures is key to developing and optimizing their applications further. This review complements other published reviews on the topic by providing a careful examination of literature to gain a better grasp of the underlying mechanism of piezoelectricity with a particular focus on bioelectric materials. It also attempts to provide a summary of the key piezoelectric biological and traditional materials, their differences, applications, and limitations, as well as a brief overview of the current state of the piezoelectric development. Review provides a resource for the basic understanding of piezoelectricity to aid further development of piezoelectricity applications in the future. So, the fundamentals of piezoelectricity. Piezoelectricity is a linear electromechanical coupling phenomenon. This means that when mechanical stress is applied to a piezoelectric material, it deforms and generates electrical charges. The process of converting mechanical stress to electrical charge is known as the direct effect. In contrast, the converse effect refers to when an external electrical field is applied across a piezoelectric material, causing the material to mechanically deform. Piezoelectricity exists in materials with centrosymmetric crystals. Out of the 32 crystal classes, 21 of them of lack of center of symmetry and are said to be uncentrosymmetric and thus are piezoelectric. Piezoelectricity is quantified by the piezoelectric coefficient D, which is the ratio between applied stress and charge, or between strain and applied electrical field, where P is the polarization, Q is the charge, A is the area. So they have a formula, and the formula goes P equals Q over A equals dx, or X equals D times E. Okay, the piezoelectricity of a material depends on both the orientation and symmetry of the material's crystal, and it can be described by third-rank tensors. The piezoelectricity tensor can be expressed as 3 by 6 matrix of component dy. For inorganic materials, the piezoelectricity is the result of asymmetrical charge distribution in the crystal under applied mechanical stress. The piezoelectricity of inorganic materials shows temperature-dependent behaviors. Above a critical temperature known as the Curie temperature, a material dissipates its piezoelectric and ferroelectric properties. In other words, thermal motions can induce changes in the polarization of the material. On the other hand, the piezoelectricity in inorganic materials arises mainly from reorientation of permanent molecular dipoles under an applied stress that results in the alignment of the dipoles in a particular direction that yields a net polarization. Inorganic piezoelectricity, single crystalline ceramics. Materials are divided into two groups: piezoelectric single crystals and polycrystalline ceramics. In 1880, the Curie brothers were the first to identify quartz as a piezoelectric crystal. After this initial finding, a noticeable alternative, Rochelle salt or potassium sodium tartrate, was discovered in 1922 and found to exhibit a higher piezoelectric strength than that of quartz. This salt was substituted by the introduction of ammonium dihydroxygen phosphate. Owing to different ferroelectric phases in titanate, their piezoelectric effect is considerably higher when compared to quartz. In ferroelectric materials, the piezoelectric magnitude and the direction can be altered by an application of an external electrical field. The remaining polarization after electric field application removal is called permanent polarization. And upon mechanical pressure, this permanent polarization generates the piezoelectric output. Recently, zinc oxide has received a particular interest as a sustainable piezoelectric material. Zinc oxide produces hexagonal piezoelectric crystals, which have a low dielectric constant and room temperature for this metal oxide has a piezoelectric effect due to an asymmetrical Wurtzite crystal structure and large electromechanical coupling capabilities. When zinc oxide is fabricated in a nano rod wire configuration, it has a heightened sensitivity due to a large surface to volume ratio, which makes it a great material for sensors. Based on the line zinc oxide nanowires, piezoelectric nanogeneration can be done. Okay, even though the NG output is initially just enough to run a nano device, such as a molecular electronic memory device, zinc oxide nanogenerators have undergone a lot of development and now show a stunning piezoelectric coefficient. Such high piezoelectric coefficiency, a wet chemical co-precipitation method was used to dope Zn nanorods with neodymium. Now, polycrystalline ceramics is another way to get piezoelectricity. Polycrystalline ceramics possess many crystal structures that are randomly oriented and only become functional after a polarization step. This often includes the application of a high electrical field to align the material's dipole moments through a process known as electrical poling. The structure of a ceramic material is influenced by the synthesis methods, which are generally divided into wet chemistry methods such as soil gel and solid state synthesis. Wet chemistry methods generally have the advantage of more efficient mixing, producing more homogeneous materials and significantly lower calcination temperature when compared to solid state synthesis. Despite these advantages, solid state synthesis is the most commonly used synthesis method due to its ability to produce ceramics with better piezoelectric properties and being less complex than wet chemistry methods. All well-known piezoelectric ceramics include lead zinc. The high piezoelectric potential is what makes it a particularly attractive energy harvester. It also exhibits ferroelectricity as observed by characteristic hysteresis loops. Hysteresis. However, the brittle nature of PZD limits its applications. It is prone to fracture due to a high Young's modulus of 50 GPa and a tensile strain maximum of 0.2%. Practical testing under applied electric fields have indeed shown a tendency for PCT fatigue cracking in a brittle process with little or no plastic deformation, owing to the high strain demand. An alternate lead-free piezo ceramic is BATIO, another ferroelectric material. The piezoelectric capacities of BATIO were discovered in the early 1940s, and the material was soon considered as a potential piezoelectric transducer. However, it was initially overshadowed by PCD, which showed better piezoelectric properties and a higher TC to BATIO ratio. So I really just wanted to I told you about the non uh, organic materials, but here is the organic materials which carry or conduct electricity, which is the main crux of what I was saying. Okay, organic, inorganic, halide. Perovskites are materials with the crystal structure of calcium tynate, which is known as the perovskite crystal structure. They consist of two cations tight bonded together by an anion. Instead of high fabrication temperature for ceramics, a low temperature OMHP fabrication is achieved. Another interesting capability, namely illumination dependent piezoelectric response, was found in a methyl ammonium lead halide, in which the piezoelectric output varied from different illumination. It was suggested that the illumination enhances the MAPBI dielectric constant and forms a considerable photo-induced piezoelectric dipole, which could play a role in energy harvesting by perovskite solar cells. Despite the high piezoelectric output, the same ceramic disadvantages apply for OMHP. They show brittleness and flexible properties, which in bulk form, and to overcome these limitations, future studies could use thin film configurations on flexible substrates. Organic piezoelectricity. Organic molecules, such as polymers, can exhibit complex dipole moments, giving rise to polymer-based piezoelectricity. Polymers are excellent materials for piezoelectric devices due to low cost solution processing, low temperature processing, low toxicity, and high chemical stability. This review divides piezoelectric polymers into two classes, namely bulk polymers and polymer composites. Bulk polymers generally require mechanical stretching and pulling to exhibit significant piezoelectricity. The applied electrical field affects the orientation of positive and negative charges, and dipoles, and consequently induces a piezoelectricity. This class of piezoelectric polymers mainly includes poly and polyamides. Piezoelectricity was first reported in 1948, followed shortly after by reports of piezoelectric polymers, and that's a polycrystalline polymer with many head to tail arrangements of polymer chains in a zigzag form in the crystal grains. Consequently, dipoles are parallel to one another within adjacent chains. This dipole moment is what leads to the piezoelectricity. There are four crystal forms. Unfortunately, only the beta form has piezoelectricity. Despite this relatively low output, the intrinsic properties of PVPDF creates an opportunity to overcome the disadvantages of bulk inorganic piezoelectric devices. These include simple synthesis, high flexibility, and adaptable design. The device exhibited is a maximum open circuit voltage. Piezoelectricity in biological materials. It is thought that piezoelectricity of biological materials has physiological importance. For example, it has been shown that piezoelectricity of bone influences its remodeling and growing according to Wolff's law, which describes the direct correlation between bone structure and the stress as it is subject to. Cellulose. The plant kingdom is a rich source of aligned materials, and there has been a long-standing interest in cellulose as a piezoelectric material. This interest stems from the known, albeit weak, intrinsic piezoelectricity of wood. While individual cellulose chains have a clear dipole, cellulose microfibrils in plant cells are aligned in an anti-parallel fashion, leading to a cancellation of the macroscopic dipole moment. Following the evidence of a large permanent dipole moment in cellulose nanocrystals, much effort has been devoted to extract and to align and order these into materials with bulk piezoelectricity. So they're getting it from plants, they're learning to do it from plants. And amino acids and crystals are piezoelectric. But this was just part one. I'll come back and read part two. I'll see you soon.